take a look at this graph. It looks quite unique, I would say. We haven't really seen this graph before, and it looks like it would be tricky to graph it and its equation and stuff. But worry not. Welcome to my channel. Today we're going to be looking at logarithmic functions, and what you saw back there was a log function, and we're just going to be looking at what log functions are and how they look like and how we can graph them and generalize them. So this is how a log function looks like. This is how it looks visually. This is just the simple y is equal to log x kind of thing. So that is how a log function looks like visually. And we can see there is like a vertical asymptote at x is equal to 0. So this is the general form of log functions, which is x is equal to p um, to the power of y minus b plus a. Now, as you can see, there is no log over here, but later on I'm going to show you how this is the same as another way we can write this where we do have the log. So over here, let's see what these variables mean. So the a is the vertical asymptote. So this is the thing that the graph is really trying to approach, but it just cannot make it. This picture shows you a horizontal asymptote, but the opposite of it, if the line was at like x is equal to 1, that would be a vertical line down, and that is a vertical asymptote. The a also controls the horizontal shift. Then we have our b, which is our vertical shift. So this is going to control how high up our log function is or how down it is. And then our p controls our steepness, or like our scale factor, really, how stretched out our logarithmic function is or how narrow it is, kind of. So let's have a visual look at this on Desmos and see how each of these variables kind of control our log function. Log general form, which is here, but I just wanted to show you that this is the same as writing this over here. So if we wrote y is equal to log p x minus a plus b, that's the same as writing x is equal to p to the power of y minus b. It's kind of just a little bit flipped around. It's the same thing, and as you can see, these graphs exactly overlap each other, so they're the same thing, but it's just different ways of writing it. So I just wrote it like this because this is similar to the exponential graph, which if you just switch around the x and y and the b and a, then that would be the exponential graph, and I feel like that kind of similarity can help us quite a bit sometimes. So as we can see, a controls our vertical asymptote, so it's basically a value the graph is trying to reach, but it just cannot reach, right? It's trying to approach that value, but it cannot meet that value. So that's our vertical asymptote, and it moves it horizontally as well. And then we've got our p, which is kind of like how stretched out this is. So as p gets bigger, this kind of angle over here gets closer and closer to 90. And as we stretch it out further, it just extends even more. And if I went into the decimals, into 0 point something something, it flips around like that. And then once we go into negative, it all breaks because we cannot have a negative base in a log. That doesn't work. So that's why it doesn't exist. Then we've got our b, which controls our height, so how high it is. Now, there's an easy way to find b. So let's say a was 5, right? So going from our asymptote, from our vertical asymptote, we're going to go 1 unit across to 6. And then we're going to check, so let's say b was 2. And then we're going to check what is the y value at that point. So as we can see, when we go 1 unit across at 6, our y value is 2. So that is why our b value is 2 as well. And you can see that is controlled by this. So when it's 4 over here. So that's how we can kind of play around with our logarithmic functions. Alright, let's have a look at how we can generalize logarithmic functions. And here we've been given this little shape, which is x is equal to 2 to the power of y plus 2, and the domain is 4 is less than or equal to x, which is less than or equal to 10. And here we're just moving around the shape. It's going to be the fixed shape, translation only. So we're going to be using our knowledge of a and b from the general form. This formula right here, and this is what we've been given. So now we're going to use our values of a and b to kind of manipulate and translate the shape. So over here, this is how our answer is going to look like, and I will show you how I got to that answer. So to start with, I'm just going to copy this and paste this into a new section. So now let's start manipulating it. So first of all, let's figure out the horizontal shift. So we want to make this move around, and we want to be able to control how much we're moving it around. So remember, our movement is controlled by A, which is, unlike our exponential, we're adding it over here, so kind of outside. So as you can see, now we can right, we can move this across. Not yet. We'll be able to soon. Sorry. We need to fix the domain for that. That's why it wasn't working. Because right now the domain isn't fixed, and that's why we cannot see what's going on. So let's just work on the B, which is the vertical up and down. Now I know A looked like it was vertical, but it's actually not. Once we fix the domain, I will show you what I mean. So for B, we want to be able to move it around. And remember, in the general form, it was given to us as p to the power of y minus b plus a. So remember, we've got our b as negative. So that is why we're going to take away our b so that we can easily move this around. Now we need to work on our domain. So the thing is, we want to maintain a width of 6 because there's 6. 10 minus 4 is 6. So we want to maintain that throughout our shape. And since we're moving it across, we're only looking at horizontal right now, so only the x-axis. Since we're moving it across by a, we want to maintain that shift. So we're going to have 4 plus a, because that's going to be our starting point, and 10 plus a, that's going to be our finish point. Again, there's only going to be a difference of 6 between these two values. And we need to have 4 plus a because our original shape started at 4, so that we can actually do it from the original shape and not move it around too much. So now let's look at how this looks like. So I'm going to move this around. See that A is controlling the horizontal shift now, and the B is controlling the vertical shift now. So it was all up to the domain as well. So now if I play this, you can see this kind of moving around, and it's pretty cool. It's pretty cool in my opinion. So that's how we can translate the logarithmic function. Alright, now let's look at how we can scale the same function. So we're going to be scaling it this time. The shape is going to be the same, but we're going to use something called proportional scaling. And let's see how we can use that technique so that we can just scale this up and keep the log function's shape as it is. Shape that we've got. So to do this, I'm going to be using proportional scaling. So we need to scale horizontally as well as vertically. So in order to scale horizontally, we divide our x by c. Wait 1 second. I'm just gonna copy and paste this on a new line. So we've got x divided by c, and to to proportionally scale up vertically, we need to divide y by c as well. So now since we just want x on this side, we can send c on this side. So we'll just have x is equal to c multiplied by all of this. Okay, now something to note is that I prefer k, so I'm just gonna write k instead of c because k is what we've been working with. So right now we've got this kind of shape over here. Now, if we look at this, what's really happening is that it's moving around a lot, and it's not starting at 4, 0, which is where it should start if we're scaling it up, right? It should be scaled up from 4, 0. So that's why what we're going to do is go ahead and take away 4. What this does, and I'm just going to keep 4 and make this 10k. So now what this does is it's kind of stuck at 4. It's not going to be moving around. And when we didn't have that, it's just that it was moving around way too much, and it was just a bit weird. So when we do minus 4, what this really tells the graph is that since this is, remember, this is going to be our horizontal shift, so that's why we need to leave it at 4. Now, something else we need to kind of note over here is that this graph keeps moving up and down. But what we really want to make sure is that when y is equal to 0, we want our x to be 4. So right now, in this equation, when y equals 0, then this becomes 0, 0 plus 2 is 2. So 2 squared is 4, and then 4 minus 4 is 0, and k times 4 is 0. So actually, the origin becomes 0, 0. But that is not what we want. We want it to start at 4. So that's why we're going to add on 4 so that when y is equal to 0, then x is equal to 4. And this is why we get this beautiful graph over here. Now, if we did remove this wouldn't work. That's why we need to have this minus 4 over here so that we can really settle it over there, and it needs to start from there. And now, as you can see, it can get scaled up. And what I've done in this version, which is the one here, I have added our translation as well. So I've added it on everywhere. So now we can move this as well as scale this. So that's pretty cool in my opinion, and that's what I've really done. So that's how you can scale a logarithmic graph, and I hope this all made sense to you. Thank you so much for watching. Bye!